So we are going to talk about the Marr-Hildreth edge detector, and this is one of the good edge detector historically, as I told you last time. So, but the basic operations are similar. So it will do the smoothing by Gaussian to remove noise, and then after smoothing, we will get S function, and then we will apply Laplacian to that. So with Laplacian is like a second derivative x and second derivative y, and then and this Laplacian is used in lots of different areas, and then we'll find the zero crossings in the Laplacian. So as I told you, the idea is that you can find a gradient, you can find first derivative and find the maximum of that. That's what the Sabel or pivot edge detector will do. Or you can find the second derivative and find the zero. And as you have learned in calculus, if the first derivative is maxima, then second derivative has to be zero. And so that's the idea here. So now we will find out if the zero crossings, where they are, and we will scan the image from each row and each column, and wherever there are zero crossings, then we will declare that edge point. So there's a difference between zero crossings and zero, because if the intensity is constant, if you find its derivative, it will be zero, as you know. If something is constant, the derivative of constant is zero. But zero crossing means that there is a function which is positive, then there's zero, then there's a negative. So that's called zero crossing. So we have to make sure that you need to know the difference. Okay. So so that's the kind of at the high level what the Laplacian Gaussian edge detector or the Marr-Hildreth edge detector will do. So the main operations are that we want to smooth. As we were talking about, Gaussian is a very good filter for smoothing, and then we will find the change, and that change is found by using the Laplacian. So the smoothing is again this convolution operation that I is an image, Gaussian is a filter, we convolve this or apply a mask, we get S, and this is the expression or equation of a Gaussian as you have been looking at this. And this is actually a plot that you can plot this in 2D, and then after that we want to find out the Laplacian of that. Okay, so that is what this is showing here, and so the Laplacian, as I said, is that we want to find the second derivative with respect to x plus second derivative with respect to y of this filtered image, which is S. We started with I, we apply the Gaussian, we get the new image called S, then we find the second derivative of S with respect to x and second derivative with respect to y, we add it up, that's called Laplacian of Gaussian. Okay, so just for these notations, as you see that if it is like this, then it is a gradient or first derivative. If it is up like this, then it is a Laplacian. These are the notations, these are the convention we will use, and everybody uses that. So now how do we derive the expression for Laplacian Gaussian? So the interesting thing about convolution is that we can do this several ways. One is that we can take an image I and apply the smoothing, apply a Gaussian filter, which is shown here. Take the image and apply a Gaussian filter. Then we get the result and we got Laplacian of that. That's one way to do it. Other way to do it, that we can take a Gaussian and find its Laplacian, because this is the expression we have. We can differentiate with respect to x, differentiate with respect to x again, differentiate with respect to y, differentiate with respect to y again, add it up. So we can do that also. So this is exactly same as this, theoretically, and you can verify that. So if we do that, then this is what we are going to get, because taking the Gaussian expression, we will differentiate with respect to x, then again with respect to x, and similarly for y, and this is what will look. And again, it's good idea for you to do that yourself. Take the Gaussian and do that and verify that this is expression you get. Now if you plot this Laplacian Gaussian edge detector, it will look like that, which is shown in the plot. And this is like inverted, it's called Mexican hat, inverted Mexican hat. It looks like that, So you have a high in the middle or negative, and then it's changing, smoothly around that. Okay, so Gaussian is this, and then the parameter of Gaussian is the standard deviation, which is the parameter that you can select what is the standard deviation you are going to use. As we told you, the size of a mass will depend on that. If sigma is 1, then you have to have at least 7 by 7 mass, because after 3 sigma, then Gaussian will almost die. And so you have to have 3 on this side, 3 on that side, and so on. And so if you take the different values of x, and I think we went through that, but I'm just repeating again, then you can plug that value in this. Of course, you select this value of sigma, in this case 1, then you will find the value of g of x, and that's what it will look like. For value of x is equal to 0, this whole thing will become 1, x is equal to 1, it will become 0.6, and so on. So this is again a mask of a Gaussian filter in one dimension with sigma is equal to 1. Okay, it looks like that. And then you can do the same thing for take the value of sigma is equal to 2 and do the 2-dimensional Gaussian. And you will take different values of x, different values of y, and this is expression, again fix the value of sigma, and then you plug in this formula, you will get these values, and you can multiply by some constant, I think here it's 255, and get all integer value. So it's better to have integer value in the mass when you apply, because the image is integer value 0 to 55. So there's no real number, and that's what this mask is. And that's what the mask, as I told you, in the MATLAB F spatial, you can generate mask like that, okay? This function. So it looks like that, and now this is the Laplacian Gaussian expression as I showed you before. Again, you can generate the same mask for the Laplacian Gaussian, So again, fix the value of sigma, take the different values of x and y, and get this, plug in this expression, you will get these values here. So here, the x and y is 0, here's x is 1, y is 0, and so on. These are the different, here x is -1, -2, -3, these are the coordinates as we went through before. So now zero crossings, as we said, this is very important. It's not a 0, but 0 crossing. And when you have an image, we will have these different cases. One pixel can be positive, and next pixel can be negative. So, which means there must be somewhere in between a 0 crossing. So that's one case. Other case can be that, well, one is positive, next one is 0, then it's a negative. That's a real 0 crossings. Okay, or it can be other way. It's negative, positive. Again, that's a 0 crossing, and then negative 0, positive 0 crossing. So these are 4 different cases will occur, and which all of these will be edges. Okay, so the other thing is that we have to look at that how strong is this 0 crossing, which reflects that how much is the change. So if the slope of the 0 crossing, suppose if it's go from A to minus B, then we have to look at the difference between A to minus B, absolute difference. Suppose for -2, and then it becomes 2, so the difference is 4. But in other cases it may be -30 to +10, the difference is 40. The slope is so that will be also used as like a threshold for, as we are looking at the gradient. Well, there's a change, but how much is a change? How strong is a change so that you can get the good edges? So same way if it is zero crossing, but how good is, how strong is the zero crossing, and that's considered by the slope. Okay? Yeah.
The slope here, are we talking the angle that is formed?
Yeah, I mean it is basically, see the, yeah, I mean you have one pixel some value, next pixel another value, so you are kind of connecting those and finding a change, which is like absolute value here. I'm showing you. If one is A, other is minus B, then you are looking at the difference between them. Okay, so it's just how much the change. So to make an edge, we'll compute the difference or slope, and we will find out, apply a threshold to that. So that is essentially Laplacian Gaussian. So now, as we discussed earlier, that we can look at the separability property of a Gaussian, which is pretty useful, which means that, see, when you apply this mask as you saw is a 2D mask, it's X and Y, it's 2D bars. So if the mask size is n by n, so in that mask we'll have n square elements. Okay. So if you want to apply this two-dimensional mask, for say Gaussian to filter, then you will have to do n square multiplication, because that's what you are doing, pixel by pixel multiplication, the mask value in the image, as I explained to you. So now, good thing about the Gaussian is that you can break it up to one-dimensional masks, and you can significantly reduce the computation. Okay, so so this is the way you will do if you have two-dimensional mask. So you'll just convolve with this, and you will get the result. Okay, now this will require n square multiplication per pixel. Now the property of Gaussian is that you can actually separate this out. You can take an image, apply one-dimensional Gaussian around each row. Then you get a result, which is after this. Then to the result you apply the one-dimensional Gaussian along each column. And the result you will get is really exactly the same as you applied a two-dimensional mask, which is this way. But the advantage of this is that you are doing each one-dimensional mask takes an n multiplication. You are doing twice as a 2n. So that's a big advantage. And that's why Gaussian is good, because it's separable. Okay? So so that's, this is your Gaussian mask. So you will apply this to the x with every row, and you will apply this, which is shown here, and you will apply this one, just make a column out of that, same mask, apply it to each column after the result. Okay, so that's very, very good property of Gaussian, and that's why it's preferred. So now it will be nice if we can do the similar thing for Laplacian of Gaussian. I mean, this we could do just Gaussian filter. So with Laplacian Gaussian we can do reduce the multiplication, but not to 2n, but we can do 4n. 4n still is better than n square. Okay, so the as I said that there are different ways we can apply the Laplacian. First we can smooth the image and then compute the Laplacian, or we can compute the Laplacian of Gaussian and then smooth and so on. So now that requires the n square multiplication, because every time we have the n by n mask. Now what this will do, using the separability of Gaussian, that we can do like this. So we take the image and apply the first derivative of Gaussian mask around x direction. We get the result, which is shown here. Then apply the second derivative, the first derivative, just the Gaussian mask to the result. So this is one we get. Then we will apply the this is the second derivative of Gaussian. So we take an image, apply the second derivative of Gaussian, because Laplacian contains second derivative, get a result, then apply the Gaussian to that. And then we have another operation where we have an image, apply the second derivative Gaussian y direction, and then apply Gaussian again, and we add that up is exactly same as we are applying the the Laplacian Gaussian two-dimensional mass. So here, as you see, we are doing the one convolution, which is one dimension, another convolution, which is one dimension, so there are two convolutions, and this third convolution and the fourth convolution. So we have 4 1D convolution, which gives you 4n multiplication as compared to n square multiplication, and that's the advantage. It's not as good as just Gaussian, but here we can still save, and that is the idea of this separability. We can separate because the Laplacian is not separable, but Gaussian is separable, so we are finding the property using that. Okay, so separability. So you can explain this thing in graphically. So you have an image, and if we just want to do Gaussian filtering, we apply the Gaussian filter in X, then we Gaussian filter in Y, and we get a filter image, which is the two-dimensional Gaussian XY, but we are doing two multiplication, two one-dimensional convolution. That's simple. Then Laplacian Gaussian, we will take an image, we'll apply the Gaussian second derivative in the one dimension, then we will apply the Gaussian in the y direction, just the Gaussian, and then we get 1 here, and then we will take the same image, apply the second derivative Gaussian y, which means along column, then do the Gaussian in the x along each row of the result of this, and then we will add it up, it will become Laplacian Gaussian. So one convolution, second convolution, third convolution, fourth convolution. So that makes it 4 convolution.
Why we are doing Gaussian for y or x?
Yeah, so that is a good question. I was expecting somebody will ask. So there is inconsistency, I just realized, between this and what I just explained to you before. And one of them is wrong. Okay, so tell me which is correct, which makes sense.
This one?
How about anybody else? Any other person? This one is correct?
Yes.
I think this one is correct. This one, other one. Because see that when you find the first derivative of Gaussian with respect to x, second derivative of Gaussian with respect to x, of course you need to apply the gxx, which is correct, in x direction, okay? But the Gaussian filter, you are going to apply in 2 dimension. So therefore you already apply Gaussian filter in x, so here you need to apply in y. So this is correct. And similarly here, you apply the second derivative Gaussian in y, which is correct, but then to filter in Gaussian, you need to apply here x. So that is correct. So there's an error, and we need to fix that. So then we want to look at, say, given an image. So this will be after we apply Laplacian Gaussian filter to that. This is the output you will get, and regardless of whether you apply 2D mask or you apply 4 1D mask, you'll get exactly the same. So now we will then take this and find 0 crossings, and wherever there is 0 crossing, we will make these dark, otherwise not. So this will give you some idea about where the edges are in this phase. Okay. So, and of course it depends on what is the sigma value. So these are the different output as sigma 1, sigma 3, sigma 6, and these are the 0 crossings at those. So this sigma is also called the scale, and we'll talk a lot about that, the scale thing, throughout the course. So, so the algorithm now is that we will compute the Laplacian Gaussian. We'll use 2D filter, or you will use 4 1D filters, as we just talked about here, and find the 0 crossing from each row, find the slope of 0 crossing, and apply threshold to slope and mark edges. So that's the Laplacian Gaussian edge detector. Okay. Now, the important issue is that, what is the quality of these edges? So first thing is that whatever the algorithm you have, it needs to be robust to noise. If there's a noise, as we talk about, noise can be due to elimination, due to lens problem, due to texture and so on. So that's important. And also we need to localize an edge. If the edge is at a given location, but if you don't detect exactly the same place, suppose the edge is at x is equal y and x is equal 2 and y is equal 3, that location image. Then if you detect an edge actually 1 pixel on the right side, not exactly that. So the edge is then not localized. So ideally we want to get the localization of edges. And it may happen that we miss some edges, or we may have additional edges. Actually there's no edge point, but we get an edge. So those are kind of factors which will impact the quality of edges. So here's the example. The true edge is like this. So each of this pixel shown red is an edge point. Edge point means there's a change. There's on this side is one intensity value, on this side is other intensity. They differ, so there's an edge. As we say, this should be an edge, because there's a carpet and there's this wood thing. So that's a true edge. Now it may happen you will get edges like this. So each pixel is declared as an edge or not. It is the blue one, and it's not really a good output because we miss edge here, but it was detected here. We don't have any edge here. This was detected 2 pixels from there, and so on. So now this one is okay, but then there's a poor localization because this should be here, this should be here. Okay. So I do want to mention one thing, that these slides I'm using. Suppose these slides, my former PhD students, who is a professor at Ohio State, Alper Yilmaz, he prepared, and then I'm using his and improving those. So that's why I put the name, both names. And that is, I think, one thing which is happening, which is really good for learning, that through the internet, through these digital media and so on, so we can leverage these slides and material from other professors. And actually we'll be using slides from other professors, not necessarily also Alper, but just want to give a credit to Alper, who did a very good job. So this is another example where we have all the edge pixels which are in the red, but then we have lots of other responses which are incorrect. Okay, so those are the problem. So in that context, there was a new edge detector, Canny edge detector, which was proposed by again a student at MIT who was doing masters around the same time where Laplacian Gaussian edge detector was proposed by Hildreth. But Canny was working with another professor called Mike Brady, and so Canny actually did a PhD in robotics, and then he's a professor at Berkeley now. So now, so he came with a different approach to find edge detector. As we talk about Marr Hildreth edge detector was motivated by human vision system, neurophysiology, and all this thing. But he came up with more engineering and more mathematical approach. He said, well, we want to come up with the optimal edge detector, which should have these criteria. First is it should have good detection, which means the optimal detector must minimize the probability of false positives as well as false negative. False positive means it gives you an edge, but it's not an edge. False negative means it missed the edge. So that's called false negative. So that is one criteria, and he came up with some mathematical form of that expression which he want to optimize. And second criteria was that it should localize an edge, as we talk about, that the edges detected must be as close as possible to the true edges. Okay? And then third was that there should be a single response to some single response constraint, which means detector must return one point only to each edge point. There should not be multiple points. So these were the criteria were used by Canny. It's a very nice thesis, and you can access that to come up with formulate this problem as an optimization problem and come up with automatically what should be that filter, what should be that edge detector which give you this optimization. And the interesting thing was that he came up with the gradient of Gaussian is the optimal edge detector. So that's called Canny edge detector. And so there's a relationship. One is that it has the Gaussian as a filter, same as a Laplacian Gaussian. The difference is that the Canny edge detector, you have a gradient, which means first derivative. And in Laplacian Gaussian, you have Laplacian, which is second derivative. So here you look at zero crossings. In Laplacian, here you look at a maximum in the gradient. They are related, but then there are advantages of using Canny as compared to Laplacian and Gaussian because you will get some false edges in the Laplacian. Okay, so so the steps are very similar. That smooth an image with Gaussian filter, compute the derivatives of the filter image, and find the magnitude and orientation of the gradient, and then apply non-maxima suppression. So that was the new thing which was added, and that make a lot of difference in the Canny edge detector. Okay, so and also the last one, which was even more important, what is called the hysteresis thresholding. So there were actually two thresholds we used. So in detail, smoothing is by Gaussian. You know, you have been looking at this. Take an image, apply Gaussian filter. You can apply 2D mask. You can apply two 1D mask, and which is shown here, and the derivative. So you want to find the gradient of the image. So this is I as an image and Gaussian G filter. Once you convolve it, then you apply the gradient of that. Or you can first apply the gradient of G and then convolve with I. So so normally what we'll do, we'll have two masks, one for the first derivative in the x direction, Gx. Another mask will be first derivative in the y direction, Gy, and we convolve with the image. We'll get two, the Gx and Gy, or Ix and Iy, it's a gradient, and then we can find that gradient. So that this is a Gaussian, and the first derivative Gaussian will look like that. We are differentiating with respect to x direction, and the first derivative with respect to y will look like that. It will be just rotated version. And so then if you have an image like this, then you will apply this Gaussian first derivative with respect to x will look like that. This first derivative with respect to y will look like that. And then from there, you'll compute the gradient magnitude and the direction, as we have been talking about. Like a Prevet and Sobel, that's what we do. The only difference there is that we don't do Gaussian. We just find the derivatives, and we do some averaging. So here we are applying the actual Gaussian filter, which is better. So that will give you a magnitude, that will give you a direction, and this is an image, and this is a gradient magnitude. And so now important things in the Canny edge detector. One is the idea of non-maxima suppression. Okay, and you need to listen to this carefully. So essentially, you know, from the term it applies that we want to suppress the non-maxima, suppress the pixels which are not maxima, which are not local maxima. Okay, so here is an example. So suppose the image is like this, and so we will look at the change, say in this direction, and we want to essentially look at the neighborhood of each pixel and see if that is above the threshold from the other neighboring pixels, because we are expecting that if there's an edge, you know, there cannot be, it has to be a maximum in the local neighborhood. It cannot be, it cannot be similar to the other pixels, you know, in the terms of gradient, because then you will get thick edges and so on. And that is the idea here. So we are going to suppress the pixel in the gradient magnitude which are not local maxima. Okay, so and the way we are going to do it will be important. We can look at a pixel, we look at 3 by 3 neighborhood, and in this we'll have 8 other pixels. We can compare with all 8, but that's not correct. What we are going to do is use this direction information to suppress. So let's say this object like this, and this is the edge here, and the direction of gradient is always perpendicular to the edge. This is the gradient. Okay, so so let's say this is the point xy. We want to decide whether it is a local maxima or not. Yes, xy. So we are going to look at in direction of the gradient, like is shown here. We look at the pixel x prime y prime on this direction, and x double prime y double prime on this direction. If this is a real edge, then it has to be maxima. It has to be more than x prime y prime and more than x double prime y double prime. Okay, because that's the idea. If there's edge here, if you look at this direction, it has to be maximum. So that is the local maxima. We want to say if the gradient at this edge is greater than this and greater than this, then that is, we will maintain that. If not, we will suppress it, which means we'll make that actually 0. So which means it won't have a chance to become an edge. So that's called non-maxima suppression. We will suppress those pixels gradient which is not local maxima. Okay, it's pretty simple, but here's the point, that this is the first time we are using the direction of a gradient to detect edges. Laplacian and Gaussian, there's no direction. It's just a magnitude. And what we did in private operator, Sabel operator, we did not use direction, even though we have the direction, because a gradient. Gradient is a vector, we'll have direction, you have magnitude. So that's the point here. Now, so if you take the real example like this, then this is the magnitude here, and this is the after the non-maximum suppression. Then on that we can apply a threshold, and we say these are the non-maxima. As you see, many of these are cleaned up here. Then we can make these edge points which are above some threshold, and that is the output. Okay, so now there's one more thing which is also very interesting. It is called hysteresis threshold. So as we have talked about Privet and Sabel, we just fix one threshold. We say, well, if the gradient magnitude is above this, it's an edge, otherwise not. Very simple. We just do this for the whole image. But hysteresis threshold is interesting, which was used by Canny, is that we want to say that if the gradient at a pixel is above high threshold, we will say it's an edge. Now, if it is below low threshold, then it's not an edge. So we have two thresholds here: high threshold, low thresholds. Okay. The third case is if the gradient magnitude is between high and low, we are going to say that if that edge is connected to some pixel which is above high, then we are going to make that an edge. So we are using this connectivity of edges, because edges don't occur isolated. They are part of edges. There will be lots of edge pixels here. So that really helps us, and that is called hysteresis thresholding. So let's first look at what we mean by connectedness. So if I have a pixel which is shown in the center, then if I use 4 connectedness definition, then this pixel connected to this one, this one, this one, this one. Left, right, top, bottom. That's called 4 connectedness. And then this is 8 connectedness, where it's connected to all 8 neighbors. And there's actually 6 connectedness and so on. So there are different versions. But you need to make sure what you are using. So once you know the connectedness definition, so then here is the idea. So let's say the edge, physical edge is like this. This is the edge. Okay. Now when we got the gradient magnitude for each of the edge, this is a gradient magnitude. Okay. So this gradient magnitude. So now, and there's this other edge also here. So the question is that typically we'll say, well, let's pick some threshold. Let's say we pick the low threshold. Then we say all these which are above that edges, so we'll get this one, all it, but we'll get this small noisy edge, which is not actually edge. It wasn't there due to noise, but just somehow the gradient got it. So that's wrong. There'll be a problem. Now, other thing is, well, we'll pick the high threshold, which will get rid of this noisy edge, but then it will get rid of this whole portion, because it's a low high threshold. So therefore, one of the thresholds is not going to work, either low or high. So we are using both thresholds, low and high. So we are going to say, well, this is below high, so we are not going to use it. And this is above high, we'll take this, we'll take this. Now, since these are connected to the one which is above high, and they are above low, we are going to make that also. So that way we'll get the right one. So which is pretty interesting, and it works. Okay. So we use two thresholds, high and low. If it is below low, there's no way it can become an edge. If it is above high, it will always become an edge. If it is between, if the edge is connected, because see, as you see that this is below high, but this is connected to this, is connected to this, is connected to this, and this was above high. So therefore, all these ones are actually declared. So that's the way we can select these edge points, and which was pretty interesting. So that is called the hysteresis thresholding. Okay. So the way it is, you will scan the image from left to right. The gradient magnitude at a pixel is above high threshold, declare that an edge point. Then recursively you look at its neighbors, and then if the gradient magnitude is above low threshold, select that as an edge point. Okay. So this is the after non-maximum suppression, and this is just to apply one threshold, high threshold or low threshold. And this is when you apply hysteresis, the high threshold and low threshold, you'll get these kind of results. So that is the Canny edge detector. So two main things, the hysteresis threshold, non-maximum suppression, and actually the third one is the gradient as compared to Laplacian. So you need to look at these things to learn more about, even though I've covered everything. First is in my book, link is given on the website. I have whole chapter 2 about edge detection, covered lots of these concepts, and there is also here in this book if you want to know more about. But I think I have covered all these things in this one so far. Okay, any questions on this part? Yeah.
You can cite the threshold value.
Yeah, so that is, I think, important thing in computer vision. That's what you have to determine that what should be the threshold value. Now, one is that if these numbers are normalized between 0 and 100, so you can say, well, you want really very strong edges, then you can have threshold above 90 or 80 or something, and related to that you can have the low threshold. But if you don't have any other information, so this is like a percentage, give you some idea and how strong edges you want and so on, then you have to do this manually, that you have to you as a human, you want edges, and you have a number between 0 and 100, you want to decide, say, well, which number it should be. So, which is fine, that most of the time you want reasonable edges, you can put, say, 80 or 70, and most of these time you will get good edges. But there's no easy way to automatically determine the threshold, and that's a big issue, is still unresolved, and people are working on that. Okay, any other question, comment on this edge detection? Yeah.
Can you go to the previous slide?
This one?
Previous one.
Just tell me the stop, huh?
And when you
Yeah.
Between low and high, that's the best edge detection, or above high?
No, see that typically you will have either you say that if it's above high, then that's a very strong edge, and say you will pick this one, this part,
But
and this part.
It's going to be because of the gradient magnitude, or because
Yeah.
of the threshold you apply?
No, I mean, so this is the gradient magnitude value. So this pixel has this much gradient magnitude, this pixel has this much gradient magnitude. So it's a plot, okay? And this one has low gradient magnitude, this one has even lower. So these are the gradient magnitude values, the way I have shown, okay? So what I'm saying, that if I apply a high threshold, and don't use this hysteresis, then I'll say, well, oh, this is above this threshold, this pixel is above threshold, I'll get this, I'll end here. Then in this way I'll end here. So this will not be declared as edge, okay? Of course this will not be declared as edge. Now when I say, well, if it is above low threshold, but it's connected, so this is all above low threshold, as you see those here. So it's connected to the pixel which is above high. These are all connected, see? So therefore I'll take all of these. So that's the idea. Okay? Yes?
When you say connectedness,
Yeah.
you mean the connectedness of pixels?
Yeah. See, remember I showed you here?
So then if it's connected indirectly, is it okay?
No, it is. Yeah, that's right. Because see, this connectedness is recursive. See that, so like this pixel is connected to this one because this is connected like that. But this is not connected at all to this one. There's a big gap. So that's the idea. Connectedness means it has to be a nearest neighbor. Then it has to be nearest neighbor like that. Okay? Yeah.
What happens if we have an edge,
Uh-huh.
and the edge have some lost pixels? So
Yeah.
if you have an edge and
Yeah, so it's a disconnected, so then you will have problem. So if suppose this piece was like this, up to here, and there was a gap here, and then it was here, and gap here, then you won't be able to select that, because this thing is not connected at all to this one because there's a gap here.
is there a way to know that that edge corresponds to the other part of the edge?
No, because see, because you are using definition of connectedness and doesn't fit in. There's no edge. It's not connected. So you are done. So that's a problem. So you have to have some pixels which is connected to the pixel which is high. Then you can get it. Okay. Yeah.
If the low threshold here intersects with the curve we have here,
Yeah.
then it's bottom of the low, then we don't consider the...
Yeah. You are saying low threshold is higher, or
Yes.
okay? Yeah. So low threshold is higher here. So still this will not be selected because this is not connected to any pixel which is above high. So still we won't be able to pick up, and which is fine. That's a noisy one.
What about if the low threshold intersects with the curve we have here?
This one?
Yes.
Yeah. Now what will happen that then we will miss a piece of it, So because this will be below low. So we have to have at least above low and then connect it. Okay? So that's, you got it? Yeah. So this is nice. It's pretty intuitive and makes sense. Okay. So let's we end this lecture.